So you've got a few things going on.
I do.
I'd like to hear. So whatever you're
Yeah.
comfortable revealing.
Yeah, for sure. It's probably an understatement. I got a few things going on. Life is crazy. Life is
I know.
crazy, but
It
but
certainly is.
yeah, but it's good, man. I mean, the best thing I got going on is I'm talking to Randall Carlson right now. So that's
Ducks.
that's pretty freaking cool. Not that many people can say that, actually, just me and Beckett. So it's pretty freaking cool. But yeah, man, I released an episode with Zahi Hawass today. So that was pretty awesome on the Matt Bell Limitless channel. So it was his only other podcast that he's doing in the States while he's here. He's in North America, so the US and Canada for 3 months actually, and he's doing all these lectures and book signings and stuff. I think he's doing 30 of those. But yeah, we were able to meet and go to dinner, and he's an interesting character. He's about like you would, like you would think, but there was some really there was some really good information to come out of the conversation, and some new stuff that just dropped. And so it's such a small channel. I mean, it's growing, my channel, but it's not gonna be like international news, but I feel like it should be. So being able to talk about it on your show today is meaningful because it'll get out to more people. And the bits of information, I guess one of the big things is that we're going to be exploring the big void within the Great Pyramid, and that's probably going to be happening in January, possibly February.
Wow.
It was, as of a few months ago, it's supposed to be in November, but I guess it's gotten pushed back by a couple of months. But yeah, basically, I had the opportunity and have the great honor of being able to be a part of the team. I'm funding the robotics component of the investment in order to explore the big void. So I jumped all over that opportunity and get to be a part of that team that goes and actually experiences it as the big void within the Great Pyramid is being explored by robotics next year, so early next year. So
you'll be taking. I think this will be your first sojourn in Egypt.
you got it. Yeah.
It's pretty mind blowing.
Yeah, no doubt,
Yeah.
no doubt. Yeah, I've kind of held off on going because I knew that, or planning a trip because I knew that this was going to be, coming
Sure.
up. So, yeah, it's going to be freaking cool, man. I mean, like to get in there, it's like one of the biggest chambers and one of the biggest places I think in the world that people want to know what is in there. What's
So tell me more about the big void. I mean, wow, the big void.
Yeah. So the big void is the size of two semi trucks, and it exists within the Great Pyramid, and it's above the Grand Gallery.
Above the Grand Gallery.
Yeah. So, and there's some question about whether or not it's like diagonal shape or if it's flat, like horizontal shaped. But I think the current best thinking, as far as I know, is that it's kind of like shaped like the Grand Gallery, so diagonal shaped above the Grand Gallery.
Okay.
And the question is like what's in there, and it wasn't discovered until the team of people got in and started to scan the place, and they recognized they found this big void. And gosh, that was years ago, man. I mean, you'll be able to.
Now, was this the Italian team?
No, this wasn't the Italian team. It was actually the Scan Pyramids team.
Okay, I remember that was okay.
Yeah.
We are going back a ways.
Yeah, and they explored the shaft in the Queen's Chamber and Ganbrink's door, and found that the two copper pins up there that I still don't think have a very good explanation. But this is a team that kind of broke off from that team. There's actually two separate teams now, and this is called the Pyramids team. That's called the Scan Pyramids team. Sean Whitehead and Will Westway are, I think Westway. I think I haven't met Will yet, but they are kind of the two of the leaders of this team, and then Zahi Hawass himself is the director of the team. He's the kind of the senior leader of the team. So, I wanted to make sure I didn't screw up my relationship with this group of people by having them on my podcast and throwing too much too many challenging questions out at him. But we had just a terrific discussion. And again, it came out today, and I think we went over some great stuff. But yeah, go ahead. Questions?
I'm glad to hear that. I
Yeah.
mean, it sounds to me like Zahi is more open than he used to be to, maybe, I don't know. He would seem, I don't know. I always respected him because I thought, okay, and look, you know, what Carl Sagan used to say, the famous saying, not outrageous, but extraordinary claims require extraordinary proofs.
Yeah.
And I figured there's a role for skeptics. And as long as it's a fair-minded skepticism and you ask legitimate questions and don't necessarily start from uh, the supposition that whoever you're challenging is wrong, has
Yeah.
no basis of credibility or any of that. So, um, because that's how that's how the scientific process works.
Right. Right. No doubt. Yeah. Yeah. In terms of open mindedness, I mean, he'll tell you that he's open minded, but if you ask him, what like, um, he's not open minded to the possibility that some group of people other than the ancient Egyptians during the time of Khufu and Khafre built the Great Pyramid, the Middle Pyramid, the
Hmm.
Sphinx, all the great. He's not open to that. So he's 100% in his mind, he knows that all of those structures were built by the Egyptians in the time that is, fed to us by academia. And that's a fact, and that there's no possibility that it's anything other than that. So there's not any open mindedness as it relates to that being anything
Okay,
other than
an
the truth.
older civilization.
Yeah, no possible way. Yeah,
Now I've got enough geology background and I've studied rock weathering and erosion,
right.
and everything that I've seen on the Sphinx. I visited there myself. Had a chance to firsthand study the pattern of erosion, and I came away convinced that yeah, we're looking at overland water flows, sheet flows that probably came from the west. It could have also been a rising of the Nile, because you raise the Nile 120, 130 feet, and it's going to submerge the Sphinx.
Hmm. Hmm.
That is not an outlandish claim.
Right.
And there is evidence that, yeah, the Nile River has from time to time flooded it to an extraordinary depth above its modern floodplain.
Right.
So it seemed perfectly reasonable to me to accept the possibility or probability that that was water erosion. So when you're there, I'm sure you'll have a chance to look at it yourself firsthand.
Yeah.
Um, and before you go, I could provide you with some photos and some interesting studies that might enhance, your experience when you're there, seeing some of this stuff firsthand. But
Cool.
but yeah, I came away convinced. Yeah, that's water erosion. So so then that raises the question: when would that water have caused that erosion? And there's two ways to look at it. One, water flow over a protracted period of time, say millennia, which of course then implies that the Sphinx is older, because we know, I mean, there's robust evidence going back to the 1950s that Egypt used to be relatively lush. The Sahara, the area around Giza, was a relatively lush climate, and there was tremendous amounts of water flowing. There were huge lakes, for example. The bedrock of the Giza Plateau is mostly limestone. Limestone erodes it dissolves basically under particularly acidic water.
Mm.
And this is why you have so many caves, for example, Tennessee and Kentucky. You're going to find Mammoth Cave. You've heard of that, of course. And Mammoth Cave is primarily eroded in limestone. So when you start, let's say, with fractured bedrock, which could be primarily, I guess, tectonic, which causes fractures in the bedrock, that allows water to percolate through, and that water will erode and create caves. So, you've got in Kentucky, large regions of the bedrock are almost honeycombed with caves, and that's because it's limestone. So it's not out of the question that you would have major apertures or cavities within the limestone bedrock of Giza Plateau.
Right.
Uh, and that there has been water. So the question then becomes, uh, I don't think you can explain that erosion around the Sphinx by any other means than water. I mean, I've seen many examples of wind erosion and water erosion, and I'm definitely come down on the side of water erosion. So it raises the question, when was that water there? Now, Robert, you're familiar with somewhat with Robert Schoch's.
Oh, sure, yeah,
He's
yeah.
all right. And he
Oh,
did the
and John
geological.
Anthony West before kind of invited Schoch out there.
Yeah,
Yeah.
and I did have the privilege of meeting and getting to know John Anthony before he passed, which was great. We were in Egypt at the same time, and we barely crossed paths at Karnak, just enough to wave at each other. But yeah, so it went from, Schwaller de Lubitsch was the first one who proposed water erosion on the Sphinx, and John Anthony West got his cue from Schwaller de Lubitsch, who wrote the famous 2-volume Temple and Man, actually, which is right there. I've been looking at it recently. It's a deep, dense work. But anyway, so it went from Schwaller de Lubitsch to John Anthony West, and from John Anthony to Robert Schoch, and then Robert took the ball and kind of ran with it. And I mean, I'm convinced that yes, it is water erosion. So then the next question is, when was the water? Well, the Sahara has been a desert for 5,000 years. So I don't think it was in the last 5,000 years. So was it a protracted period of time, like several millennia, or was it a singular event? Now that I don't have an answer to, but it does look like there have been major flooding events in Egypt, particularly back during that Younger Dryas window. Evidence of extreme Nile floods and so on.
All over North Africa. I mean,
all over North Africa.
Yeah. Evidence of flooding all over. But yeah, if you ask Zahi, there is zero chance that it's water erosion. Zero chance.
What does he think it was?
He says it's wind. He says it's wind. I know.
No, there's no way.
There's no way.
I'm sorry.
Yeah, like I'm not I'm not going to be as close-minded and take that to zero, but man, if that's wind erosion, doesn't that have to be like 1,000,000 years old? Or I mean, it's like it's for wind to do that to limestone within on the Sphinx means that limestone all over Egypt would look like that. If that's really what wind does to limestone. I mean, there's trillions of tons of limestone blocks all over Egypt, and none of them look like that.
None of them look like that.
Right. So it just doesn't make any sense. The whole thing.
Not to me.
No.
But I think that we will find there are going to be other examples. The Osirian. Robert makes the argument that the Osirian is much older.
Yeah.
And if you bury something, or you take the limestone, you sheathe it in granite. Now, granite is not going to erode like limestone in water.
Right.
But we can look at. I almost am tempted to pull it up here. I've done some interesting research on the quarrying techniques. Now, when I was in Egypt, I didn't have time to visit quarries. Next time I get back, that's going to be high on my list, because when you look at the quarries in Egypt, particularly the limestone quarries, going back to the Old Kingdom, the erosion on some of the walls are so slight that you can still discern whether they, the pick marks and the chisel marks. Yet, if you look at the surrounding enclosure of the Sphinx, in some places 1 to 2 feet of limestone material has been removed.
Mm-hmm.
I'm tempted to pull something up here just to look. Do you have, by any chance, anything you want to share on your end?
Yeah, we do actually. So that was one of the things, that the big void is going to be explored. That was a big drop that we had. And then the second thing was that there is a third chamber, or a second unexplored chamber, that's been located within the Great Pyramid, and that we don't have plans to explore that one yet. But that was something that he dropped on our show that I guess he's also mentioned on his lecture tour that he's doing, but that there's another chamber that has yet to be explored. It's not as big as the Big Void, but that was something else. And then Ryan, if you could pull up for us the graffiti that he also talked about on the show. So there's apparently Randall been graffiti that has been discovered by Zahi's team up within the relieving chamber, so-called relieving chamber of the so-called above the King's chamber, and that there's more graffiti that says basically Khufu's gang was here. So yeah, this is what he found, and there were, I think, Ryan, correct me if I'm wrong, but I think there were like 3 different sets of graffiti. Is this maybe is even all 3 of them? But he said that he found them in multiple rooms above the King's chamber, and by rooms he just meant little compartments. But yeah, apparently it says that Khufu's people were here, and it was like the 13th year of his reign or something like that. But it still is not conclusive proof that Khufu was the one who created the pyramid. I mean, these could have been. There was that we also talked through that piece of papyrus that talked about the Torah limestone that was being brought over during Khufu's reign, but that certainly could have been just an exterior renovation. And these people that were part of Khufu's team could have just been, in the pyramid doing work or doing renovations or whatever. So there's still no conclusive proof in my mind, even after talking to him for a couple of hours. I mean, it's like you find all this evidence and like you want to fit it into your narrative, but it's just evidence. It's just a theory. I mean, it's a good theory, but it's not necessarily that like we have all the answers just because we found some ripped up piece of paper that said that Khufu was quarrying and transporting Torah limestone, which is so yeah, but I mean that was a pretty big deal. This picture right there that he showed on the show was a pretty big another pretty big drop of information, it felt like.
So Zahi's team discovered this graffiti?
Yeah.
Okay.
Yeah, and he has no motive, I mean,
I wouldn't. Okay.
But no, I'm sure they really did. I'm sure it's brand new graffiti. I mean, I'm sure it's like brand new discovered graffiti. I'm sure that he didn't like forge it, but again, it looks really old, but like it could have come from Khufu and they could have just been doing renovation, I mean, I think that we just need to remain open to the possibility that it was created at a different time. That we don't necessarily know that for sure, and it just feels like the Sphinx. I mean, that it's just much more likely than not that the Sphinx is significantly older. So why wouldn't the pyramids be older?
All right, aerial view of the Sphinx, and then we see the Sphinx ditch here. On the west side, you can see the rounded forms of the limestone exposed here. Let's go to the next one here.
Just win.
So, yeah, and here you can kind of see the in the background here, and the Sphinx temple in the valley, temple in the front here, with assuming that these blocks, these megalithic blocks here were quarried, because Matt, that the original Sphinx is mostly it's bedrock, and a yardang is an outcrop, this limestone outcrop. So there was this yardang emerging from the sand at some point. This is the assumption, and that makes sense to me. And that was what was carved into the head. And then the blocks around the body were quarried away in order to expose, from roughly the neck down of the Sphinx.
Randall, pull that mic a little closer for me.
Sure. Okay, you got it. Okay, so then this is an exhausted New Kingdom limestone quarry, and note the traces of the stepwise removed blocks. I wish I had a person standing in here. You could see this is actually, you see this doorway and you think, oh, this is 6 feet high, but this is really, these layers here are like 3 feet, each of these. So a person standing here is going to be relatively small. But this is New Kingdom, and this is essentially the Egyptian method of stone quarrying by means of separation trenches. The assumption is that they're using chisels to remove the rock between each of the separate blocks. And here would be a cross-section profile. Here you can see the stepped profile. This is your working trench here, and then this block is removed, and then this is excavated. And generally what they'll do is they'll look first for natural bedding planes, because that provides the easiest way to separate the blocks, right?
Mm-hmm.
So here's a cross-section profile of what a pre-quarry pre-excavation quarry would look like. And they're just, you remove the overburden to get to the bedrock, to the limestone, and then each block is successively removed. And this is kind of what you're left with here. Is once those blocks have been removed, you've got this stepped profile. You'll still see stepped profiles in modern quarries, right? So here's, this is stone pick marks on a limestone quarry from Ramesside times, roughly 1200 years BC. So you can see very prominent. The pick marks have not been eroded away. Here is stone pick marks in a quarry from the early New Kingdom. So this is roughly 3,500 years ago. And again, there hasn't been enough material removed to obscure the pick marks. So for 3,500 years, this has been a desert environment, which is a very low erosional environment, right? Because there's water is the primary agency of erosion here. And then this is Old Kingdom, so this is circa 4,000 years ago. And again, you see the pick marks that are left on the quarry walls, right? So very little erosion has occurred. Now let's go back to the Sphinx, and you can see they're riven with these solution cavities. And I mean, this is textbook water erosion, particularly sheet floods flowing over the walls of the ditch here. So here is a cross-section through the west wall of the Sphinx enclosure showing the actual limestone layers. It's 22 feet in height, and basically the recession of the original quarry wall is going to be a function of the induration of the limestone, meaning how hard is the limestone. So, you know, this down here is going to be a harder limestone than number 11 right here, because this is softer limestone. It's eroded, it's recessed greater. Now here is a profile of what an original quarry would have looked like. And you can see here, this lines up nicely with the natural bedding planes. I've just taken this to scale. This is the actual diagram we looked at in the previous slide. Juxtaposing it on the cross-section of the west wall of the Sphinx enclosure, we can see that there's some nice lining up of the bedding planes, but it gives you an idea of what the original wall would have looked like the day after all the blocks were removed.
Mm.
So the erosion and the recession of the quarry wall is not going to begin until the blocks have been removed. And at that point, now the weather can go to work and start eroding the profile. And so you've got this original profile, and then this would be the end result of the regime of erosion. So it gives you an idea of how much material has actually been removed from that wall, because that wall would have been, and I don't think even Zahi would argue this, is that, you know, the blocks that formed the Sphinx temple were removed, quarried, and we can see the blocks. They're big rectilinear blocks. So there's no doubt that this would have been roughly the profile at the point the blocks were removed. And again, an important point is that the erosion wouldn't commence until the blocks have been removed. But clearly, there's erosion. You can argue it's wind or you can argue it's water, but there is erosion. I would say that it's clearly water. There's a difference between wind and water erosion, because for one thing, wind, what it does is it's going to pick up and entrain sand, and it's going to be almost like it's going to almost create a sand blasting effect. that creates a lot of pock marks and things. It's very distinctive from water. Water wants to smooth things off, round things off. Wind erosion is, like I said, it's going to leave a very granulated surface with pock marks and so on. But I think this gives you an indication of how much material had to be removed in order to get the profile that's there now.
What percent chance would you say that wind could be the culprit for the erosion that we see around the Sphinx? Is it 0 or is it just?
I would say wind has contributed some amount to it, clearly. But again, we know that for a lot of the history of the Sphinx, at least since Kefren's times, it's been buried under sand. So once it's buried, its wind isn't going to do much. I would say, from my opinion, that is wind erosion is a component, but a minor one compared to water.
Right.
And I don't know if I have them in this particular presentation, but I have a lot of photographs of water erosion, particularly of limestone. And when you look at it, it's very suggestive highly suggestive that this is water, not wind. Like I said, so this is just some stuff that I've collected in the study of limestone erosion. Limestones are highly soluble in acid waters. However, they do not dissolve equally over their surfaces, and the action of dissolution is usually concentrated down joints and fissures. The concentration of dissolution processes down joints and fissures leads to the focusing of water into such joints and fissures. And if you go back and you look at this, I mean, that's exactly what he's describing right here.
Yeah.
Exactly.
Right.
So,
so it's old.
I think it's got to be old. But now the question is again, the time frame. Because if you've got highly acidic waters and they're loaded with, let's say, sand or other grit material that could accelerate the erosion, you could accomplish a lot of erosion in a matter of, a few weeks or months easily. On the other hand, if it's a more, that's where it's at in my mind right now. Are we looking at something that's extremely old, where the flooding that produced this erosion was relatively spread out? Or are we looking at a single event or several concentrated events? I don't know. I honestly don't know. But you can get an idea. This is my approach to this, was to study limestone erosion. So here we got, this is going back to 64. This is a rate of erosion of intertidal limestone.
Let me just real quick ask you a question before you get to this,
absolutely,
Randall. So but doesn't it feel like if this erosion was taking place and it was destroying the monument, the beautiful, pristine stone monument that whatever culture of people had built, wouldn't they be repairing it and like flattening the walls out so that you didn't see all these rocks on the casing wall around the Sphinx? Like, so, I mean, just logically, it just seems like all that damage, all that erosional damage would have to be done after whatever that civilization was that built the Sphinx was no longer there, whether they were wiped out or just,
Correct.
Yeah.
Yes, precisely.
Yeah.
That's exactly how I would interpret it.
Yeah.
And then another culture later on comes along and maybe excavates, removes the sand, and
right.
It's interesting. Of course, this is totally dismissed by mainstream archaeology, but if you read Plato in his two dialogues where he addresses the story of Atlantis, the report that comes from the elderly Egyptian priesthood is that they have, they inform Solon that they have their sacred registers go back 9,000 years. Now, is that conceivable? Well, I mean, mainstream archaeology just dismisses it. It's not conceivable. We don't even need to consider that it's a possibility. But again, in the spirit of the outrageous hypothesis, I think we could go, well, let's consider, is it possible that a tradition could have been handed down for 9,000 years? I don't know how Native Americans are able to have myths and stories about great floods in North America, but they do. Dozens and dozens of them. And we know there have been tremendously great floods in North America at the end of the last ice age.
Right.
It's certainly doable. I mean, we've handed down Christianity for 2,000 years, Judaism for 2,000 years, Buddhism for 4,600 years. I mean, it's like humans can pass stuff down for a really long time.
For a really long time, yeah. So I don't reject that out of hand, that they could have had traditions passed down for 9,000 years. So if we go back to this, let's say the Old Kingdom, we're almost halfway back. Well, essentially, we are halfway back to that 9,000 years, right?
Yeah.
So is it so out of the question that they had traditions about a former civilization that could have occupied that region? Not at all.
Not at all.
And that there would, just like now, we're looking at monuments in Egypt that are 4,000 years old. Well, perhaps there were monuments that have been lost since then that were thousands of years earlier than Old Kingdom times.
Right.
And when we factor in the extent to which we know the climate and environment of North Africa and around Egypt, how drastically it's changed, it's likely that there were catastrophes that could have interrupted the continuum of civilization. In fact, I think that's at this point an established reality in my mind.
I mean, even just a couple of degrees of temperature change to mess with the crops for a couple of years, and you've completely lost a civilization. So
yeah, I think we did talk about that.
Yeah.
So this is, we don't need to get into this in great detail, but this is the kind of research I did to try to get my head wrapped around what this Sphinx erosion meant. And so this is you have limestone shores throughout the world which show characteristic erosional features. In Quaternary limestones, Quaternary would be the last 2.5 million years. Of the tropics and subtropics, there is commonly a wide, flat, intertidal platform which bounded at its landward side by an undercut cliff, the notch or intertidal nip, it's called. This type of shore profile is well developed in Western Australia. While there has been much discussion about the nature of the erosive process, surprisingly little attention has been paid to the rate at which it proceeds. So let me see, I think here, so all direct estimates of the rate of erosion of intertidal rock surfaces give figures of quite a different order. Emery in 1941, on the basis of dated inscriptions, estimates the rate of retreat of sea cliffs at La Jolla, California, at 1 foot in 600 years, at a mean rate of 0.5 millimeter a year. So now you're talking intertidal. That means it's a high energy erosional environment, right? Because that's high tide, low tide, the sea is encroaching, the surf is pounding and washing against this exposed limestone cliff. So what they were able to do was determine that it took 1 foot in 600 years. Now, this is a highly energetic erosional environment. Now, going back to the Sphinx wall, if we have a foot of material removed, does that mean it was subjected to 600 years of highly erosive activity? I don't know, but we can go on here. The shore rocks at Point Perone near Perth are mainly hard, secondarily cemented eolianite, which is wind-blown, with a high calcium carbonate content, which would be what you would find typically in limestone. Here there's a platform some 20 meters wide. Behind this, there is a typical notch. The notch here faces inshore and is thus sheltered from the full impact of the waves. To obtain a direct measurement of the rate of erosion, stainless steel rods were driven firmly into the hard rock of the notch in pairs at 3 levels above the platform. There's been no movement of the rods since they were placed. So here's a profile of it. It shows the 3 rods driven into the rock. So now what they were able to do was to measure over a period of years how much the limestone recessed, because the rod is not eroding. So it's going to recess, and then you're going to have more of the metal rod exposed, right? That makes sense, right?
Sure. Yeah, absolutely.
Note positions of steel pegs and amount of rock eroded from 1953 to 1962. And here was 2 millimeters, 4 millimeters, and 9 millimeters. And that makes sense because the lower is going to be subject to more erosion than the higher ones, because at high sea level, yeah, it's going to be eroding up at that higher level, which is here's heights above the datum. So this is mean sea level right here. This is mean sea level. So just a little bit above mean sea level, the rate of erosion was 9 millimeters. But as you get higher, it's less erosion. That makes sense, right? Because down here, the waves are washing up against this more consistently.
Yep.
So then we'll skip all this. But so at this level, the mean rate of erosion was 1 millimeter per year, a figure that is, again, very close to estimates from limestone shores elsewhere. And so 1 millimeter per year. So, 1,000 years is going to be 1,000 millimeters or a meter, right?
Right.
So that's 1,000 years of erosion would remove a little over 3 feet of limestone.
Right.
Cut that in half, you're looking at about 1.5 feet. So that's 500 years, and that's sort of consistent with the other study we just looked at. So here we can get an idea of, okay, how much does limestone erode under what particular regime of climate and so forth, and energy. We can look at others, like this is an interesting way to determine erosion rates. You look at inscription legibility method for estimating rock weathering rates. Well, if you have a gravestone, it's going to have a date inscribed into it, isn't it? Right? It's going to have so the death of that individual, and when they were buried there, they've got a grave marker. It's got the date of the death, so that's the date that stone was put out into the weather. So there's been those kinds of studies. So this Emery was the first to quantify rock surface recession rates from inscription legibility by noting that 3.2 millimeter deep carvings in the wave-washed calcareous sandstones, this is the one we just looked at, were obliterated in 6 years. So cliff retreat to 50 millimeters per century. So then on this study, here's the summary of it. The mean of several observations gave us the rate of solution about 1 inch in 500 years. So now let's just take that. Now here we're looking at an environment where it's going to be maybe 40 to 50 inches of rainfall per year, but much lower erosional energy available, obviously, than a cliff that's faced right into the pounding surf, right? So this represents a low energy erosional environment. The cliff face represents a high energy erosional environment. And here it says the mean of several observations gave 1 inch in 500 years. Now let's go back to the Sphinx. If it was just under a normal erosional environment where you might get 40 inches of rainfall per year, which is kind of what we get here in the southeastern United States, 40 to 50, 1 inch in 500 years. Well, we can see that conservatively, in some places, 12 or 16 inches or more of rock face have been removed. So let's use 12 times 500, and now we're looking at 6,000 years of erosion. So you can begin to see here, we're establishing some parameters, but whether it's a fast erosional environment or a slow erosional environment, we're faced with some conundrums. We're faced with some questions here, like, okay, if it was quarried, say 10,000 years ago, when there was fairly significant rainfall for 4,000 or 5,000 years, well, maybe it could do that over, like we just said here, this came up to 6,000 years. Okay, that's one scenario. The other scenario is you've got a high energy erosional environment, and it happened much quicker, right? So what I've tried to do in this study is establish the parameters here within which this erosional phenomena could take place. And they're very consistent. You know, limestones, their origins, distribution, and uses. The United States Bureau of Standards, they conducted an experiment because what they did here, they took 2-inch cubes of rock and exposed on the roof of the Bureau's building in Washington. And after careful weighing spread over a period of about 7 years, it was found that from exposure to the weather, an oolitic limestone would lose a layer about 1 millimeter in thickness in 100 years. The loss from a compact crystalline limestone was about 1/3 less. And so 1 millimeter per 100 years equals 3/8 of an inch in 1,000 years. Now that's in the environment of Washington, D.C. You see, it's sitting on the roof.
Mm-hmm.
This will be the last one we'll look at. I've got more, but this one was in the Tennessee River. What they were doing was the purpose of this paper is to present a few figures on the rate of solution of some limestone boulders in the Tennessee River at Watts Bar Dam. Since the limestone dissolves very slowly and almost unnoticeably to man, there is very little exact information on this subject. So in 1912 to 1913, the Corps of Engineers, United States Army, constructed a navigation dike of large limestone boulders almost in midstream of the Tennessee River at Watts Bar. The second stage cofferdam at Watts Bar, you know, cofferdam is when they isolate a part of the river to divert the flow, right? So that's what they did. They created this cofferdam, and it exposed this navigation dike of limestone boulders that had been below the river. So the river has been washing over it for decades, right? Let's see. Okay, it had been in the river for 27 years. So now they build a cofferdam. They now expose these limestone boulders to the atmosphere, and they're able to study how much erosion occurred. The boulders were quarried from a nearby source. We don't need to get into all that. It was found that pure limestone had dissolved from 1/4 to 3/4 inch more than the impure laminae, only because the impure laminae had harder stuff in it. But anyways, it is by this means that the rate of solution of limestone is established. The rate of solution of these limestone boulders is not comparable to the rate of solution of a limestone under normal groundwater conditions, but in case of free movement of the river water, as under a limestone bluff, over the limestone on the bed of the river through open joints or seams, the rate is comparable. And so here was the rate, 1/2 inch in 25 years. Okay, so let's think about that. You've got limestone boulder. It's submerged under a freshwater river. That fresh water flowing over that is going to erode it at a rate of 1/2 inch in 25 years. Let's go back to 16 inches times 25 times 2. So at that rate, water washing over the limestone it would have taken 800 years to remove 16 inches. And we'll see 16 inches of material removed from the Sphinx wall. So now you can, I think, begin to see sort of the complexity of this and some of the problems confronted. First of all, you have to go to what was the water flow? What was the volume of water flow for how long? Was it a single episode? Was it multiple episodes? Was it more normal erosion? But that in itself would imply many millennia of erosion. So this is kind of where you can kind of brings the problem into bold relief. Now, what I would like to see is some optically stimulated luminescence type dating on the exposed walls of the Sphinx ditch. Nobody's ever done that, to my knowledge, which would show. The problem there might be is because the exposure to galactic cosmic rays, which create the imprint, have been interrupted from time to time when the ditch became filled with sand. But I would still think you could get some kind of an idea. But going back to the question of water flow in Egypt.
Well, isn't it also an issue that it's been kind of probably slowly, continuously eroding over, at least the last 600 years, but probably 10,000. I mean, a problem as it relates to the OSL.
Right. Yes. But yeah, right. And I'm not an expert in OSL, but I think that give me a couple more days.
Okay.
But it seems like that could be a viable way of getting at least some estimate of how long that ditch has been exposed to the air.
Okay.
Because that's, it's being used in glacial studies because, if you have a rock that's under the glacier that's been quarried and then the glacier recedes, exposes the rock to the atmosphere, now the whole process begins at that point.
Mm-hmm.
So exposure to the atmosphere resets the atomic clock in the rocks, and then it starts creating isotopic byproducts, and then you can measure that and get some estimate.
Yeah.
So,
but it's not wind.
I don't think it's wind.
I don't think it's wind, man.
No, I don't, because, Robert's shown pictures of wind erosion, and it's very distinct. You don't have to be a geologist. If you look at a few of them, and then I can show you pictures. Okay, here's wind erosion, here's water erosion.
Right, and you'd see it all over all the other limestone in Egypt, and this place was covered with sand for thousands of years. So it's like...
Exactly.
Yeah, it doesn't make any sense.
So this is way back from 1960. So what is that, 40, 50, 65 years ago? But this was an early textbook on geomorphology.
Mm-hmm.
B.W. Sparks, he was one of the early highly esteemed geologists, wrote a textbook. And he's talking about in Egypt, all right? He says stream floods, although stream floods and sheet floods may be effective agents in the formation of semi-arid landforms, many deserts bear the imprint of even more significant water action. It seems very doubtful whether the required amount of water ever falls in present conditions, and many authorities have attributed such erosion to a wetter period during the Pleistocene. For example, the valley on the west side of the Nile at Luxor, containing the tombs of the kings, appears to be a water-eroded valley, but the tombs themselves show no signs of destructive water action. This means that water action of any significance probably ceased at least 4,000 years ago. So he goes on, but yeah, I mean, there is evidence, and it's continued to accumulate in the last 65 years since this was written, that there have been extreme periods of extreme rainfall and flooding throughout Egypt. So why is it such a huge leap to think that, the Giza Plateau could have been subject to some of these water flows?
Yeah.
I feel like I should show you some pictures here. Let's see, because just to give you an idea how impressive some of these water flows might have been, let me go to, okay, so a wadi is a water eroded channel in the desert floor that has very little water in it now, if any, except during flash floods, when you might have, every few years, every decade or so, you might get rainfall, and then the wadi will become active for a short period of time, and then it goes back into being dry. Not necessarily know how to pronounce all these words, but Wadi Firan, it's the largest oasis in the Sinai Desert. And what it is this, it's a water-carved valley. And one of the questions would be, again, how long did it take to cut this valley? I'll go through and show you a couple of more here. So here's a photograph, and this is the Wadi here. It's a valley. It's been carved by water. And here you can see the floor of the Wadi Firan, the largest oasis in the Sinai. And you'll notice that It's a lot of boulders, right?
Right.
This is all water deposit.
That's a
here.
camel down there.
Well, that's just a little. What does it say here? That's not a real camel.
Oh, okay.
That's just a little,
Gotcha.
little icon.
Oh, okay.
So here
Thought it was literally standing on that rock. That's funny.
So here's a wadi in the Sahara Suda or Black Desert, and this is very typical. You'll see very similar formations in the deserts of southwestern U.S.
Right.
You notice the cliff face here, the material that's splayed up against the cliff face, and then the flat valley floor. You'll notice there's a whole bedrock floor. You see some of it prominent here, but it's buried out here.
And Randall, that material that's pushed up against the cliff face there, would that have been deposited there during the actual flood from the floodwaters themselves?
Okay, so when you see this kind of a formation, typically in the term that's usually used to describe it as talus. So there's two ways of emplacing it, gravity or water. Now, gravity, when that means that the rocks are falling off the cliff face and piling up.
Right.
Well, the larger the material banked up against the cliff, the more the cliff is going to have receded. And what you see in many cases is that a lot of the material, particularly, I can even show you photographs of some of the stuff that we see out in the western U.S., is definitely water emplaced. I don't know about this, but I would guess, if I had to guess, I would say it's most likely water emplaced. I'll show you, look at this right over here. You're going to see something in just a minute I'll show you, which we know was water emplaced. And you'll notice that the cliffs are pretty vertical here. They're pretty sheer.
Right.
So did all of this material come off the cliff? Probably not. And this mineral that you see, the mineral concentrations you see on the surface, would have indicated at one time there was a lot of water in here. It was probably sluggish, and then it evaporated, and if you dug down, you might have 50 or 100 feet of sediment here, and then at the bottom of that, you're going to have bedrock.
Wow.
Now, let's see. So here's another example of a wadi. Now, this has very sheer walls.
Right. So
and,
you're going to see bigger rocks and more rubble if it's gravity, and more kind of sand and dirt.
What you're going to see, look at this rock right here. If it's fallen off a cliff, it's going to have sharp edges, angular edges.
Right.
And it has, if you see this rounding, that indicates it's been moved by water.
Right.
Water will roll and tumble a rock. It'll start by breaking off the edges and the corners. Just like imagine your little lapidary unit. You throw your pebbles in there, and what comes out is smooth, rounded rocks, right?
Yep.
So here's another one. You can see some of the rocks in the foreground. So these have been transported. You would call this subangular because it's somewhat angular, but the corners have been eroded off right here. They're rounded. They're not sharp. And let's see. Again, you'll see massive piles of boulders. Some of them have sharp edges, so they probably were stripped off the canyon walls and not transported very far. The amount of rounding is an indication of the distance of transport. The more they're transported, the more rounder they get.
Makes sense, yep.
And here you've got this large flat floor. We can see exactly the same kind of thing throughout the evidence of the Pacific Northwest, where you had these gigantic flows, discharges of 50 to 100 million cubic feet per second. And when the water drains away, it'll oftentimes create a flat floor. Also, the natural arched bridges, which they're all over the world now, but none of them, to my knowledge, are actually in the process of being created. They're in the process of being destroyed by the modern erosional environment. In fact, there was one that I visited maybe a decade ago that recently collapsed out in, where was it? Which one was that again? I think that one was in Arizona. But it's very difficult. Ask a gradualist-minded geologist to explain the genesis of rock arches and natural bridges. Here's another one. Look at this. See these features here?
That's cool.
Yeah, isn't that cool?
Yep.
Okay, let's just jump on. Yeah, so here we have, this is a very interesting, I'll provide this if you'd like to read this. This is a very interesting study. In the journal Global and Planetary Change, reconstructing an extreme flood from Boulder transport and rainfall runoff modeling, Wadi Isla, South Sinai, Egypt. And this is where it is. There's many dozens and dozens of these wadis. And this one here is draining the uplands here out onto what would have been the coastal plain at one time. And so here you can kind of get to see, when this wadi was created, this is some of the sediment that's being transported within that wadi. So I mean, like, you look at this is a rock that was plucked from the canyon walls, transported and dumped here now picture this.
Clearly by wind, Randall. Clearly this was wind erosion here.
Well, that would have been quite a wind, at least 20 or 30 miles an hour.
Yeah,
gusting.
at least.
So picture this, a narrow channel, and the water, in water flow in hydrology, you've got a conservation of mass circumstance, so that you have a narrow channel like this, the water's rushing through it. Right now, let's say that narrow channel opens out into a basin. Well, that water that's rushing through that channel at one velocity, let's say it's moving at 20 to 25 miles an hour or more even. Once it breaks through of the confining channel, it spreads out and then it slows down. The competency of flowing water to transport sediment is based upon primarily the velocity of the water, secondarily the depth of the water, but primarily its velocity. Now, when it breaks free of the confining channel, it both spreads out and it slows down. So at the mouth of many mountain, river, creek channels and valleys, so on, you will see a fan delta, it's called, splayed out from the mouth of the channel, right? And you will see that as you go up towards the mouth of the channel, the sediment will be larger. It can be boulders, but at the distal end of it, it could be finer pebbles, even sand, or even silt, right? So what's happening is this guy is standing right at the mouth of a wadi. So as this water is breaking loose from the confinement of the channel, it's dumping its cargo of sediment. Now let's go to the next one. Look at this boulder. So this is a boulder that has now been transported in the water flow. So that is a pretty substantial flow of water. So how do you get that? Well, it had to have been rainfall, extreme rainfall somewhere, up valley. There was a rainfall. Now, this is probably over the highlands there. We saw you go back to the map here, right here. So you have rainfall over the Sinai Massif. And then that runs off. It collects in these channels. It runs off. But there's enough rainfall that the flows in these channels are enormous flows, very destructive, highly catastrophic. And then the French term is debouche. When that water debouches out onto the plain, it dumps its cargo of boulders. So you can see this here. Here's where you can see it's emerged from the confinement of the channel, where it would have been very much deeper, but once it comes out onto the plain, it shallows, and this dashed line shows the water level, and that's probably 50 feet above the valley floor, and then it begins to dump its cargo. Now notice this giant flood-rolled boulders. So looking at this picture, you see the boulders. Those boulders were stripped from the quarrying or the excavation of the channel, the wadi. So behind him, you see a cliff. In front of him, over on the other side, there'll be another cliff. So the water flow excavates the cliff, entrains the quarried boulders, sweeps them down current, and then once the channel begins to open up, it dumps that cargo of boulders. Okay, now compare that to the next picture, which is a picture of me taken in southern Idaho.
How fast is the water traveling to move those boulders?
Oh, probably 40 to 50 miles an hour.
Yeah. Okay.
So it's moving fast.
Yeah.
But take, just for comparison, look. It's the same phenomena.
Yep.
This is Idaho. This is the Sinai.
Yep.
And like across from me is another cliff like this one, the counterpart. Before this water flow happened here, there was not, this cliff didn't exist, right?
Right.
I'm on a boulder bar here that's 3 miles long and hundreds of feet thick. In fact, I just took a tour group out and we visited this boulder bar a few weeks ago. This picture was taken, I think, in 2000. I'm younger there. Early 2000s. When was I there? It was 2002, 2003, something like that. So I took a group of 38 people back. This is one of the sites we visited. And I wanted them, and again, look at this is interesting. Like, look at this boulder. You see there's a sharp edge right here. So this boulder was quarried, it was rolled, and somewhere before it was dumped, it had enough of an impact against it that part of the rock broke off.
Okay, right.
So you can see that right here.
Yep.
And as you go, you'll see that most of these rocks are rounded, but a lot of them, because again, this is a very violent thing that's happening here, and these rocks are rolling and tumbling. So they're not only getting rounded off, but at some points, many of them will break and fracture. And
what type of rock was that, Randall? That wasn't basalt, was it?
This is basalt,
Yep.
yes.
Okay.
So here we have what are called imbricated boulders and cobbles, and water will do this very distinctive type of stacking. The analogy I use is, imagine you've got a bookshelf with books on it, right? I can almost turn my camera here and we could look at my bookshelf, but you'll get the idea. If I push it this way, it'll tilt, you see?
Yeah.
If I push it this way, the books will tilt this way. Well, the water will do the same thing. It'll take these rocks and it'll stack them like that. And that's what you see here, right? So you can look at this and you can see the direction of water flow is indicated by the black arrow. See, just imagine that that the force of the pressure of the flow is coming from the left towards the right. And this is in Wadi Isla, if that's how you say it. This is in Montana. And you're seeing, as you look at this, you can see the same type of imbricate structure. And the water flow is from right to left. Here you can see imbricate boulders in the southern Appalachians. And once you've recognized this, you can, you understand the process. So looking at this, you don't even need the arrow, do you? You would know that the water flow is from left to right.
Right.
See that?
Yep.
And then you have masses of alluvium, which is where the finer grained stuff is dumped in thick layers. And again, look up here at the top, Matt. You'll see this big old boulder up here. The way to understand what you're looking at here is this is a dried out gigantic mud flow. A mud flow. And this is in Wadi Isla, Egypt. And then this one is in the Mojave Desert of California.
I think it's Isla.
Thank you. Isla.
Isla.
Yep. That makes sense. Mm-hmm. Okay. From now on, for the rest of my life, I'm going to know how to pronounce that word. Isla. That makes sense.
Isla.
So yeah, you notice what are called the hoodoos here, and you'll see the same thing right over here.
Right.
So after the emplacement of this mud flow, it dries out, and then overwash will carve these hoodoo-like features here. So,
That's cool.
Yeah, it's cool. And,
Yeah.
and it's literally like a language that you can learn. And I'm trying to teach people how to read this language because there's an epic story writ large into the surface of the entire planet that we live on.
Right.
And now, we've got things like this. We can look at, we've got photographs. And when I took this was, God, this had to have been more than 20 years ago when I was exploring this channel here. And interestingly, this led from the Mojave Desert, and I was able to trace the water flow through a succession of canyons and basins that held former lakes. All of this water ended up in Death Valley, and it literally filled Death Valley 1,000 feet deep. It's called Lake Manly, and once you begin to realize that the world we inhabit is the whole planetary surface has been sculpted by these tremendous events, gigantic floods, ice ages, impacts, huge volcanic eruptions, tsunamis. The list goes on, and we realize, my God, the model of Earth change now is way beyond the gradualist models of a half century ago.
Right. Right. Yeah, no doubt about it. Yeah, it's fascinating stuff, man. And I guess, it just seems like we ought to be able to very soon, probably a lot sooner than we think, plug in videos and images and just overview of the terrain of wherever we want to, all over the globe, North America, into AI, and say, what happened here?
Yeah.
And just have it spit out like, okay, there's a 98% possibility that that this is from the glaciers rapidly melting or whatever the hell.
Right.
Yeah, it shouldn't be long, I think, that there's global agreement upon our human history and what these, like, it's one there's very few people that can actually read the earth and the images of the earth and look at rock formations like you can, and it feels like AI should be able to help us be able to actually spread some intelligence amongst humanity that you already have, that you've had for decades now, and be able to really come to some conclusive agreement upon what happened and where.
Well, working with Beckett has already opened my eyes to the possibility of AI. We've done some very preliminary reconstructions of like glaciated landscapes, meltwater discharge coming off the glacial front, creating landscapes. So this was just, a few weeks or a month ago we did this. And I mean, I knew the potential was there, but working with Beckett, I was like, boom. Yeah. Oh, wow.
Right. It's going to change everything in just a couple of years. I mean, when you show the images of the Sphinx to AI, and I told Zahi this, it spits out, and you take out archaeological bias, it spits out 9,000 to 12,000 years old as the age of the Sphinx.
Really?
Yeah, like every time. I mean,
wow.
Yeah. I mean, that's every time I do it. And every time I ask AI, like, if you take out archaeological, I mean, just try it, after the show, see what it says to you. And it's like, yeah, that thing's, it's 9,000 to 12,000 years old. And Zahi's like, oh, I don't believe in AI. It's like, okay.
Well, that's a convenient way to.
Yeah.
I don't believe in AI. Okay.
Right. I don't believe in intelligence. So yeah. I mean, it's it's pretty fascinating, and I think like that's just the beginning, though. When you start, those are images. I feel like when you start to, like, you survey the entire surface of the planet, of the Earth, with with LiDAR and with ground penetrating radar, and you start to like get sonar on the coast, and you start to just feed all the satellite imagery that we have of the Earth into AI, and you say, look, tell me about the history of the Earth from a geological standpoint, like what happened. I feel like it ought to be able to paint a fairly accurate picture within the next couple of years. And so I feel like I hadn't heard anybody talk about this, but I feel like that's coming, and that like we're on the brink of really understanding a lot.
I absolutely think you have to be right. And I think we are just on the threshold of developing entirely new models of the Earth, global change, the history of the planet. And where to me is so fascinating and relevant is when we start understanding the nature, the extent of global change during the period of time that we humans, modern humans, have inhabited this planet. And it's been extraordinary.
Yeah.
Just extraordinary. And there's so many things that I'd love to talk to you about in further depth. I'm sure we'll get an opportunity coming up in a few weeks at the Cosmic Summit. One of the people there that would be worth checking out is Dallas Abbott, who's been in the forefront of doing research into mega tsunamis around the world and the evidence for gigantic tsunamis. In some cases, with run-up heights of over 600 feet, which means, that's essentially a measure of how high the wave was when it made landfall. And that's beyond the capacity of a volcanic eruption or even a large earthquake. You're probably getting into...
It's extraterrestrial, right? I mean,
yes, it certainly does seem like that.
Yeah.
And so
like an impact. I mean, like a comet, like a...
Correct. Yeah. Or an asteroid. You got something like if you got a half a kilometer object moving at 20 miles per second, which is realistic.
Yeah.
That slams into the ocean. Yeah, you're going to get... And here's the thing. When you look at, like, if it happens during the Ice Age, you had a much greater exposure of the low-lying coastal plains around all the continents.
Right.
So your run-up... with a tsunami, you've got two things to consider. The run-up height and the run-in distance. Now, obviously, if you've got a steep terrain, and you can still have a 100-foot wave that comes in, but it's not going to go far inland. But if you've got a very shallow plain, that can wash inland many, many miles. So you've got the run-up height and the run-in height. During the Ice Age, a tsunami could have a much greater run-in distance because of the exposed shallow coastal plains. Like right here and I'm sure it would have been roughly the same in Florida. If I go here over to like Savannah, on the east coast of Georgia, I'm right there standing at the beach, and if I'm suddenly transported back to the late glacial maximum 15 to 20,000 years ago, sea levels are 400 feet lower, and the coastline, the beach is going to be 50 miles further east, and I'm going to be standing in the middle of the forest.
Right.
Mm-hmm. However, again, that coastal plain is low gradient, so any tsunami making landfall has the potential to wash in a lot farther because of that.
Right.
But then, of course, what happens is with sea level having risen 400 feet, and that rise in sea level, we were just talking earlier about the energy expended at a intertidal zone, and its erosive work on limestone. Well, during a 400-foot sea level rise, we now know that sea level rise was not a continuum, a smooth rise. It was pulsed. There were meltwater pulse 1A, meltwater pulse 1B. I think there's a third meltwater pulse that we're going to soon be able to identify that coincides almost exactly with the lower Younger Dryas boundary. Because the work of not Roy Breckenridge, work on the Mackenzie River and the meltwater floods into the Arctic Ocean seem to be dating right at the lower Younger Dryas boundary.
Okay.
So yeah, we're kind of on the threshold, I think, of unraveling a whole and creating a whole new model of Earth history.
Yeah.
And once we have that as the context, we should then can take a fresh look at the human story within that framework.
Right. I was just thinking how incredible it was that humans could be hunting that much during this time period.
Yeah. Well, and then that brings us, of course, to the question of the mass extinction of the great megafauna.
Yeah, that's what I'm saying. That they overhunted them all while all this incredible climate changes and sea level changes and meltwater pulses were all happening.
Yeah. So, it's. I'm going to show you a quick graph here.
Do you find that academia now is kind of just ignoring this period
Oh yeah.
as opposed to like they used to strongly say, overhunting is the story, and like we know what happened and it's just gradualism and there's no catastrophe. Now it seems like they're all like, I don't, it's not really my area, I don't really want to talk about it. Like it feels like they recognize that there was that they're going to have to change the story here, and that it is probably best just to distance themselves. That's kind
Yeah.
of what I gather from just listening to various people on the
I think your impression is accurate.
yeah.
Although I've gotten a lot of communications over the last few years from geologists, some of them saying that they think I'm right on some of my stuff. I've gotten emails and comments and things from younger geologists or college age, in their 20s, that are going into geology. And like, I got one not too long ago. He was saying, I used to think geology was so boring, but I started listening to some of your podcasts and seeing some of the evidence you presented about great catastrophes, and I found it so interesting, I've decided to go and get my degree in geology.
Yep.
So I think that it'll take another 5 to 10 years, but I think we're going to have a whole new crop of young scientists who are much more willing and not so invested in the gradualist model.
Right.
And there's many reasons, and a lot of them get into politics, and we won't need to discuss that today, but at some point, it's a discussion we need to have.
Mm-hmm.
Now, have you ever seen this graph, the oxygen ice? Did I show this to you?
Yes, I believe you mentioned this when you were on my show, yeah.
I mentioned it, but I might have not shown it to you.
Okay.
Okay, so, and if you don't really remember, then it's good to revisit it. So oxygen isotopes in Greenland, we don't need to get into the technology, but basically, the heavier, you've got oxygen 16, oxygen 18. In an energetic environment, in warmer weather, there's more energy to evaporate ocean water. That more energy means that more of the heavy oxygen can get evaporated and then precipitated out as rain or snowfall. In colder times, you don't have the available energy, and so what happens is the ratio of oxygen 16 to oxygen 18 in rainfall and snowfall changes, because less oxygen 18 is being lofted out of the oceans, right?
Mm-hmm.
So when it's cold, you're going to have more 18 to 16 in the oceans. When it's warm, you're going to have more 18 relative to 16 preserved, for example, in ice cores. And that's what's going on here. So shifts to the left mean cold, shifts to the right mean warm. Okay. So this is the last, you look down the vertical side here, you see 10. That's 10,000 years ago. And this is a depth of 1,500 meters in the Greenland ice. So 1,500 meters of ice have accumulated in 10,000 years at the summit of Greenland. And it, like it's showing here, it shows temperature constantly and repeatedly warming and cooling 2 to 3 degrees Fahrenheit or more. Right. Now, look at this little spike down here. This is called it was a 200-year roughly cold spell in the middle of the post-glacial climatic optimum. It was possibly 3 to 4 degrees, very sudden cooling. If it happened now, it would cause major disruptions to agriculture and agricultural crops and food production. It would probably, in fact, severely stress civilization. This was a century or two of really cold weather. And then notice something here as we come up closer to the present. Notice that the magnitude of these oscillations increases. Now, if I turn this on the side, you could actually see that that the climate has cooled since what's called the post-glacial climatic optimum. During the climatic optimum, temperatures worldwide were 1 to 3 degrees warmer than now. Sea level studies, and I've got dozens of them, show that during this warm period, sea levels were 3, 4, 5, even 6 feet higher than now. This is well established, but again, this is not being talked about because it doesn't fit the paradigm, because there's a political agenda now which wants to make people believe that anything that's happening now in terms of climate change or environmental change is the consequence of human activity, primarily the burning of fossil fuels, right? But yet, when we look in the past, what we discover is evidence that completely contradicts this model, that previous to the Industrial Revolution, the climate was steady state. It most certainly was not. And this Holocene graph right here shows that it has regularly oscillated every few decades up to 1 to even in sometimes up to 2 and 3 degrees. But what's interesting is to me, really interesting is when we get down here to about the 1,500-meter depth, 10,000 years ago, we see the graph trailing off to the left. Well, the reason is it's the last phase of coming out of the Ice Age, right here, the last most recent Ice Age. So if I go to the next slide, I've just taken that's what we just saw, and this represents climatic change over the last 10,000 years. Now the ice core goes down to bedrock, and it goes back 250,000 years, right? So now let's take a look at evidence for what kind of climate changes were going on prior to the Holocene, which the Holocene is the modern epoch. It's now dated to, interestingly, to 11,600 years ago. It's associated with meltwater pulse 1b, and coincidentally coincides with the Egyptian story of the 9,000-year sacred registers prior to Solon's time. Remember, Solon visited Egypt in 600 BC. Add the 9,000 years to 11,600. Look up the inception of the Holocene, 11,600. Look up meltwater pulse 1b, 11,600. So now let's go back 250,000 years and see what the climate was doing.
Yeah, it's crazy.
It's crazy.
Yeah.
How come we're not talking about this? Well, because it doesn't fit the narrative. Something was going on here. I mean, you want to talk about global warming? Look at this down here. This is the so-called Eemian, marine isotope stage 5E, right here. Sea levels were up to 40 to 50 feet higher than they are now during this warm period right here. Greenland ice cap, no more than half the mass of it was melted so much back that it actually formed two distinct ice masses with a huge conduit between them. You could travel across Greenland from east to west, where now the ice dome is. That's how much the Greenland ice sheet melted during this period of the Eemian, which is dated now to 116,000 to 139,000 years ago, 13,000 years, half of a precessional cycle. And that was the Eemian. What in the world is going on here? Is that the sun? I don't know. I think Robert Schoch would make an argument, a strong argument, that this might be solar induced. I don't know. But we need more studies unburdened by the constrictions of political narratives and politically driven agendas to address questions like this. What is the norm? Is this the norm, or is this the norm?
Well, for glacier versus interglacial, I guess, right?
This is interglacial. We've got interglacials. Look right here. This is the Younger Dryas. This spike to the left, you see right here?
Yep.
That's the Younger Dryas.
Yep.
So you see that the climate went through a spasm of warming right here, and that spasm of warming is meltwater pulse 1A, 14,600 years ago. Then it slammed back into full glacial cold, and then there was a second spike of warming here, and that's meltwater pulse 1B. And you have these two rapid pulses of sea level rise.
So is this basically saying that, I mean, if there's more ice on the cap, so going back, past 15,000 years or whatever, obviously the global temperatures are going to be colder, but there's going to be more dramatic, more volatile changes in temperature as when there's more ice in totality. When temperatures are lower, there's going to be more volatility.
Correct.
Yeah. And then there's going to be some events, like whether it's solar or whatever, freaking aliens or something, who knows, but that cause that huge spike from time to time. And it makes human survival in one place for extended periods of time very challenging, because the climate's constantly changing, and so the food that the animals that you hunt, or the whatever food that you're growing, or whatever trees exist or plants that you're eating or shrubs, it's going to change. So it would be obviously more difficult to establish, some.
Yeah. So 2 key terms here: resilience and adaptability.
Right.
They were masters of adaptability, our ancestors.
Yep.
To survive a couple 100,000 years of what we just saw. Now, the critic would say, "Oh, well, that's just Greenland. That's only local." Well, no, it's not local. We know now from proxy studies from all over the planet. Was it uniformly severe everywhere? No, because there were some places where the effects of global change were milder. Now, if we look at using as our proxy the loss of species at the end of the last ice age, right? So you got over 100 species of megafauna went extinct, and that could be 120. It depends on how you divide the species up, but just for round numbers, 100 species, probably more. Where was the greatest concentration of species loss? North America. And a very close second was South America. So North America and South America both lost in the ballpark of 3/4 of megafaunal species. And a megafauna is an animal over 100 pounds in body weight, about 44 kilograms, right? So North America, South America lost 3/4 of all species over 100 pounds in body weight. Eurasia was about 35%, and Africa was about 10%. How would you interpret that?
Solar impact into the Americas.
Something.
I mean, not solar, but like like a comet impact into. It's something that hit the Americas harder than it hit the rest of the world.
Something, we'll leave it undefined for now, although I would certainly lean towards an impact event as the most likely candidate.
Yeah.
But yeah, so what happened was America lost most of its large megafaunal species. Africa lost the least amount. So when you look at Africa, the Serengeti Plain, and you're seeing the rhinos and the elephants and the hippos and the giraffes and the water buffalo, the big animals, most of those are the Pleistocene holdovers.
Right.
Didn't go extinct.
Right. And it could be in part that Africa's climate and terrain and the food sources that were abundant in Africa, just because of the type of food and climate and terrain that exists within Africa, that it was more hardy, and that it just survived, and that it was a bit more delicate in the United States and in North and South America. And but yeah, it definitely seems like it hit closer to home over here.
Yeah, I kind of think of North America as ground zero for whatever happened. And we could do another conversation sometime. I could show you the evidence that I've accumulated that would suggest that it was some kind of an impact-related event.
Yeah, that seems like the most likely. Now you've said the end of the last ice age a couple of times, but I mean, is it really the end, or are we just in an interglacial period and going back into the same ice age?
That's a fundamental question you've just asked.
Yeah.
And that's an important question, because when we look at previous interglacials, now one of the things you got to bear in mind looking at this graph is it's been compressed, right? So if we were to stretch it out, so you had the same, the same ratios as on the y-axis.
Yeah.
What you would see is that there are interglacials in there, but most of them, with the exception of the Eemian, were shorter than the Holocene. In fact, it looks like, 5 to 8,000 years typically was about how long an interglacial lasted. And we're 10, 11,000 years into the Holocene. And this is why I think it's very important that we try to come to grips with understanding, what's going on here, what's changing.
And can't if the Gulf Stream shuts down, for example, because the Earth heats up a little bit more, or because of whatever happens, doesn't that push us back into the depths of an ice age if that gets shut off?
Well, that is an interesting question. Now, it is evidence that the ocean circulation was interrupted, right, during the deglaciation phase. But the thing you have to bear in mind is that there were gigantic flows into the North Atlantic. I mean, we're talking about billions of cubic feet per second. There's nothing like that going on now. So we're looking at a completely different set of circumstances when it looks like the thermohaline circulation was interrupted at the end of the last ice age. So I'm not concerned too much about, we don't see anything comparable to the influx of water into the North Atlantic now, like we did during those meltwater pulses.
Right.
I should have
yeah, we want to know what's next, Randall. I mean, you got to tell us, man. Are we going back into an ice age, and when's it going to happen, man?
Okay. Well, I think one of the big picture things that I look at is I think that our planet, we're part of a cosmic ecosystem. Involved changes, solar changes. It involved changes in the cosmic environment, like, for example, galactic rays seem to also fluctuate, like larger scale events, even on the galactic level, might be affecting us in our solar system. We can see that in the type of isotopic evidence, because typically in normal solar times, you got the solar wind, which acts as a buffer and insulates Earth from the direct bombardment of galactic cosmic rays, which cause spallation of neutrons, which leaves a proxy evidence like carbon-14 and beryllium-10. Beryllium-10 we can find in ice cores. Carbon-14 we find in organic material, trees and plants and so on. And if there's a sudden spike of beryllium-10 or carbon-14, what that suggests is that there was a greater influx of galactic cosmic rays, which then in turn suggests that the sun was in a period of very low activity. And so the buffering effect of the sun now has allowed, because of the diminishment in the power of the sun, the solar wind, you now have a greater influx of cosmic rays. The sun also we know from the early 90s and solar observing satellites, seems to have a much higher degree of variability than we had previously assumed. Okay, so the same thing can happen if the sun goes into a hyperactive phase. You will get proxy fingerprints that show, again, the same thing. They're different, but I don't want to get into too much of the technical explanation because we're running out of time. But clearly, there are many variables at work here, and sometimes they may work in such a way that they reinforce each other, shall we say, constructive amplification. Other times they may, mitigate each other, right? So there's a lot of work that needs to be done in sorting this out. This is why we need true science, authentic science, unburdened by political agendas, to try to understand the true and authentic environmental history of this planet.
Right.
One of the things might be, I think that in the larger framework, impact events could be behind a lot of it.
Right.
Also including enhanced spikes of seismic activity and volcanism. And we see that in this tremendous mass transfer that took place when you had 6 to 7 million cubic miles of glacial ice piled up on the continental land masses, rapidly melting and transferring back into the oceans. Two things now that evidence is emerging that there was massive seismic activity and earthquakes and a huge spike of volcanism. And it only makes sense, right? Because the pressures of transfer, removing that ice from the continents, and the isostatic rebound after that ice is removed, likewise, the transfer of these trillions and trillions of tons of weight, say, back into the oceans, you're now going to have an isostatic depression, and that's going to be concentrated along the sutures where the continental spreading is taking place, because that's the most, that those are the weak zones in the Earth's crust. So it only makes sense, and empirical data supports that there were significant vertical movements of the ocean floors during this period of mass transfer. That would cause accelerated volcanism. There could be all kinds of consequences. There could be feedback loops that take thousands of years to play out. I would go even so far as to speculate that maybe some of the volcanism and earthquake activity that we're seeing today might be residual from what happened 10 to 15,000 years ago.
Sure. Could be. Yeah.
As a possibility.
Yeah, absolutely. Yeah, it's interesting. And you know, I mentioned AI a little bit earlier, and we talked about that a little bit earlier as a way to kind of tell us a little bit about what the human past has looked like, or what the geological past has looked like. But it can probably also help us with what is the future going to look like. You know, it can probably also help us predict like what's really happening. Like what's really happening with the poles, for example. You know, like is Ben Davidson right, or is Stefan Burns right? You know, like, is there about to be a pole flip, or is this just a normal, excursion, you know, or, you know, are we headed into are we headed back into the depths of the ice age, or are we going to be in this interglacial period for, you know, a few more thousand years? It's like, it feels like, and it doesn't seem like anybody can hide that information from us, from the people. It's not like you can have a gatekeeper, or various governments could hide that, because AI is going to be out there for everybody.
Not anymore,
to use.
right?
Yeah.
Not anymore.
Right.
You know, again, if you look at the precedent, you know, the Eemian was the period that was considered to be the closest analog to the Holocene. And we now know, though, that there were major climatic fluctuations within the Eemian that go way beyond what we've seen within the Holocene. But again, going by the precedent and looking at interglacial periods, I mean, this was part of what fueled the concern in the 70s, because there was between the 1940s and the early 1980s, the climate was actually cooling. At the same time, we're discovering that these climatic changes had happened way quicker than anybody had imagined. And so the fear was that, okay, well, if the interglacials are only 5 to 10,000 years, and we've already been in the Holocene for at least 10,000 years, maybe it's all coming to an end.
Right.
I don't know.
Yeah.
I don't know. But I am definitely an advocate of more study, more scientific work. And I also believe that the testimony, the legacy of our ancestors that's come down to us in the form of myth and legends and so on is going to be highly instructive and valuable in making sense out of this. In fact, I think that the scientific record and the mythic record, if you want to call it that, are perfect complements of each other.
Mm-hmm. Yeah, to combine those and to try to understand to spit out some knowledge.
Yeah.
Yep.
Two quick quotes here. One was from this is from an editorial that appeared in Nature immediately after the publication of the graph that we were just looking at, right? This is by Richard Fairbanks. He was with Lamont Doherty Earth Observatory, and he was one of the people studying and analyzing these ice cores. Now, bear in mind that a generation or two before, the belief was the transition out of the ice age might have been a process that took 30 to 50,000 years. And then as radiocarbon dating came along, it was shortened to perhaps 10 to 15,000 years. And now we're getting the isotopic dating. We're getting the Greenland ice cores. And what we're finding there is pretty sobering, actually. And this is the quote. From measurements, and this is referring again to this graph that we're just looking at, from measurements of annual ice layer thickness over the past 15,000 years, the authors find that Greenland's climate, and we just saw the graph of the close-up I showed you of the Younger Dryas and the 2 warming spikes associated with meltwater pulses. From measurements of annual ice layer thickness over the past 15,000 years, the authors find that Greenland's climate, emerging from the last ice age, twice shifted from glacial to interglacial conditions over an astonishingly quick 3 to 5 years.
Wow.
Yeah. This is what the record of the Earth is instructing us about.
Wow.
This, yeah.
That's crazy, man.
And you ask anybody who tells you now, Matt, from now on, oh, well, the science of climate change is settled.
Yeah.
Don't believe them.
Yep.
Now, that's not to say I'm totally of the philosophy we need to be good stewards of this planet. We absolutely do. But our stewardship needs to be based upon real science, authentic science. And again, if we're here and, we at one time shared this planet with other hominid species, right? I mean, I think 14 other hominid species have been identified, all of which are extinct. We're like the last man standing.
Mm-hmm.
I think it's coming down on us. We need to be adaptable and resilient, because whether it happens in our lifetimes, I think there's no doubt these changes are ongoing. They're in our future. But I think that once we understand them, I think we can create a sustainable civilization. And this would be a topic for maybe our next conversation, is how do we take this knowledge and apply it to creating a civilization that might actually survive for millennia.
Right. Yeah. What do we need to do to create a civilization that's going to be able to survive through climate change, through ups and downs on temperature, through crop changes? Like, what do we need to get ourselves off of in terms of the supply chain? Are there, like, we go around in Florida, we're going out and we're planting all these non-native trees, and none of them produce any food or fruit, and we're pumping water out of the water table to keep all this lawn grass irrigated and all these non-native trees irrigated. And it's like, why not use regular field grass? Like, why not plant trees that actually give us food? And then, something bad does happen. We're not just stuck on this supply chain of depending on Walmart for our freaking survival. Like,
100%.
Yeah. So
I would, for years advocated and endorse the idea that, the lawn culture, I love a nice little strip of lawn. Even when we kid, we had some, we had lawn in Minnesota, and I remember hot days after working on the neighbor's farm, I'd come home and I would love to lay in the cool grass, as the sun is getting low in the sky. And, it makes a nice buffer between 100% nature and your lived in environment. But it's completely beyond. To me, it's like, hey, give me one nice little, maybe, 20 by 20, 30 by 30 of lawn. Let me have the rest devoted to food crops.
Yeah.
Imagine if in suburbia we traded out the lawn culture for growing food crops.
Right.
So
Then there's no dependence on anybody.
Yeah. And then if there's an interruption in the supply chain, it's not that big of a deal.
Yeah. I went down to Peru in the Sacred Valley and was driving around there. And, as there's not a lot of money down there, obviously, but people are growing their own food, so it's like, it's not as if people are out on the streets committing crimes. Like, it's not like they're struggling for survival from the standpoint that they can't eat and that they've got to go out and rob everybody, so it's like, yeah, people are poor. Yeah. Housing is a challenge, but people are eating, man, and like, that's such a huge part of, like, if we can't figure that out as a society, And like, but the government doesn't want us to figure out, they want us to continue to be reliant upon them. And so nobody's going to help us with this. But as a people, we've got to start realizing some of this stuff. Like
100% agreement what you just said. The government wants to foster dependence.
Yeah, no doubt.
No doubt. And I think we're moving and we want independence.
Yep.
I kind of think of it as there's a new independence movement afoot. And I want to see it. I want to see it proliferate.
Me too.
Very much so. I'm going to have to run. You probably do too, but I feel like there's a lot of conversations in our future, and we're growing an audience of people who are just, I think, hungry for these kinds of ideas. And I certainly don't claim to have the final word on anything, but I have been thinking about this stuff, studying it, researching it for over half a century.
Yep.
I came out of high school, and in 18, I kind of made a commitment to myself. I thought, I want to become an educated man. I want to become educated. What does that mean? So I set about using most of my spare time from 1969 to now, engaged in study and research and learning. And I feel like, now I don't have the final answers to everything. No, not by a long shot, but I have some insights that I think that I could share that would help those coming behind me on this quest, save them some time.
Right.
Because my mentors, the people that I looked up to, studied under, read, etc., they're basically all gone now,
Mm-hmm.
And it's a little bit scary and disconcerting when I finally realize I'm kind of on the tip of the sword right now, and it's a kind of a weird feeling, like, oh, I think I want to retire to my lair here. You see, I've created this lair with everything I want that I've fantasized for decades, and now here it is. You have to drag me kicking and screaming out of it. But yeah, there's, we're looking at possibly a tour to the Azores.
Nice.
Focused on the Atlantis story.
Nice.
But yeah, there's all kinds of things, and I'd love to keep sharing it with you. I think we've had some great discussions. This is our third discussion now, right?
Yep. This is our third. Yeah, we did 2 on my show, and this is the first one we've done on yours. And yeah, man, I mean, you are carrying the torch, Randall. I mean, like you said it, and for an entire generation, you're educating people about stuff that people aren't getting anywhere else. I know that you were inspiring to me. I might not be, podcasting if it wasn't for you. I mean, you get hit by a lot of different things in your life, but just seeing you and Graham on Joe Rogan a number of years ago, like totally opened up my mind to so many different possibilities about just, Earth's history and human history. So, no, man, you're not retiring anywhere. You got to keep educating people. You got to keep doing what you're doing.
Right. I'm looking into, protocols that might hopefully add a couple of decades. You get to that age, you're a little bit behind me, but, you get to this age, once I cross that big 7-decade threshold, I could tell the machine has got some wear and tear on it, and I need an upgrade. I need to overhaul the machine.
Yep.
I'm doing pretty good, but
you're doing great, man. You're doing great.
Well, yeah. I can do better. Yeah. So again, I hope we can keep this dialogue going. I'm really looking forward to the Cosmic Summit, hanging out with you there. I'm sure maybe we can grab dinner together one night. I'd like for you you've met Julie.
Oh yeah. Julie was here. Yes.
Jesse. Yeah,
yep.
Of course.
Yep.
They were in the studio.
They were. Yep.
Jesse, he's looking forward to the summit.
Good.
There's something interesting to talk about with him, as far as, some of the, medicinals that he's been on, and the some pretty impressive changes that we've seen in the last year. So, I mean, yeah, we got a lot to talk about.
Yeah, for sure. No, I look forward to it, man. I look forward to seeing you for sure at Cosmic Summit and getting together. My wife's going to be there as well. So, yeah, I look forward to seeing you and Julie and Jesse. And, yeah, for sure. I mean, I'd love to continue to have you as a guest. You're always one of the favorites. You're my number 1 episode. So, Your first episode that we did is the number 1 episode on YouTube. So
That's okay.
Yeah.
Well, I like hearing that.
Yeah. No doubt.
Right.
Yeah, for sure. And
All right. Well, I think maybe we can surpass that.
For sure. Oh, we will. No,
Yeah, I mean, my numbers are getting up there.
Yep.
Which is good because it's actually giving me a little more resources to work with because I've pretty much worked on a shoestring for years. All of the tours that I'm doing now that started around 6 or 7 years ago were preceded by my buddy and colleague Brad Young, and usually a small group of guys going out on our own dime, doing all the recon and exploring these landscapes for 20 years plus before it actually turned into guided tours where I'm taking dozens of people out to these sites and essentially teaching them the language of the earth. I'll leave you with this quote. It's from forget which chapter, it's from the book of Job. And it's kind of been one of my guiding ideas for decades, ever since I first encountered it. Because I love reading the Bible along with other spiritual literature, but I kind of read it from a different perspective maybe than most people. But this quote from Job: "Speak to the earth. Speak to the earth, and it will teach thee."
Love it.
Yeah.
Love it. Yeah, that's powerful.
Yeah. All right.
Yes, sir.
So,
It's a good one to end on, my friend.
good one to end. All
Yep,
right, Matt.
yep.
See you in a few weeks.
Yep. See you then. Great to chat with you, man.
So long, Ryan.
See you, Ryan. See you, Becky.
Hi, Randall. We'll see you.
Okay. Will Ryan be there at the
I will
summit?
be there.
Ryan will
Randall.
be there. Yeah.
Okay.
Yep.
So maybe we'll do more this time, Ryan, than passing in the elevator. We're getting on and off the elevator.
We'll figure this out. We'll figure it out soon enough.
Yeah, that was great, Randall. I really appreciate it, man. That was a great conversation.
It was. I enjoyed it too.